So let me give you possible method to support the complex queries. For the path queries, we are able to construct a computation graph. We need to map the anchoring entity is here. So it is gonna be the seed node. And by going through the multiple relation questions, we expect some nodes are placed in the tail position. We need to develop the embedding technique to support this computation graph. How to do that? So these are example that I gave you. And how do you answer this query? To answer the query, so one of the naive ways is we just travels every possible the path in the knowledge graph. So starting with the Turing award, by looking at the win relation, we're able to search 3 different choices. So it is just the knowledge base traversal. So using knowledge base, the graph database, we get the triples. And then to consider the graduate relationship, we get this and this and this and this. And then you're able to get this. So these are naive way, because knowledge graph is incomplete, often incomplete, or too much dense. So these are 2 extreme cases. And when it is very dense, it is not tractable to travels all the path. Think about that. We have long history about the Turing award, and we have many different, the large number of people who received the Turing award, and we need to follow their graduate schools and check out their answers, and it is not tractable. Particularly we have long the path sequence. So this is to avoid this unnecessarily the computational burden, we can use the embedding based technique, use this, and we move first to the one location in the embedding space, and then we go here. And we use the final scoring function at this space, and then we just propagate to adjust this relationship embedding in this location of this and this relation embedding as well. So this is one way to deal with the computational burden, so by using the embedding based approach. So one difference is, so major difference is computational graph, right? In this case, computational graph is from the instance space. In this case, the computation graph is from the relation space. So that is the main difference. So by having the embedding based approach, so I will give you the exact technique later. So these are the actual result, and try to give you what we can expect from the embedding based the path query processing. So from the initial query, so the anchoring entity is here. We try to respond this question: list male instrumentalist who plays string instruments. So the anchoring entity is here. So these are from the human being. So we don't extract the automatically extract this. So I mean in this paper, many following paper, the follow paper tackling the problem from the natural language, how to construct a computational graph, and automatically. So, in this paper, we focus on it is converted to the computational graph. Anyway, we start with the string instrument, and they are placed here. And by considering just one relation, we are able to get all the possible answers. So we just considering the string instrument, and it's not difficult to find the true answers, right? Just by looking at triples in the knowledge base, we are getting the perfect true positive rate. And we are interested in the instrumentalist, and we are getting some noise, but still very good, and something like this. So, but still showing a very good result by using the embedding based approach. And let me give you how we can do that. So now we have a computation graph. It could be the path and conjunctive queries, and it is more generalized form, right? Before considering this path, it is previously the path-based queries, and where we combine two different paths, so it becomes conjunctive queries. So it is a more generalized queries. And try to answer the question. And from the question, we constructed the computation graph, and we try to respond to this question using knowledge graph. And when we use the traversal based approach, we need to go through everything, right? So we gave you this is a heavy competition, and instead in the embedding approach, at first we start with the two differentiating seed entity. Seed entities are Turing award in Canada, and we get the relation embedding, which is also good projection. We now are getting to Q1 and Q2. And we need to get the intersection from the two vectors. And the intersection operations are actually set operation, right? Maybe we can employ the set-based neural networks, for example, deep set or any kind of permutation invariant set function. The simplest example is we just get the mean value from the two different vectors. So these are one example of the permutation invariant set function. So we're comparing the mean value. So we don't consider the orders. So it is also the permutation invariant set function. So we have here, in going through the relation operation, we get the answers here. And so we have the training. We do training. We have different trainable parameters, the entity embedding, relation embedding, parameters of intersection functions. For the scoring function, we use this. We have the query embedding and the answer, and we try to minimize the distance. Right? So trainable parameter, each entity has the d-dimensional information. Each relationship has d-dimensional information, and another parameter for the set-based neural network, right? the permutation invariant neural network. So for the training, it is pretty similar to the node embedding technique. We initialize the embedding for all the entities. We sample the positive pair and negative pair, and we compute the distance from positive pair and negative pair. We optimize the loss function. With the query evaluation, we given the test query, we compute the score, and we sort distance and rank all the V. Yeah, that was the initial approach, but it is not supporting the existential quantifier. So it is to additionally consider the existential quantifier, and it becomes now you can support the existential positive first order logical queries. So in this paper, they introduced previously they still based on the some point-based embedding. So every query is mapped onto a point in the embedding space, but it is multi-dimensional. But all the internal query in Q1 and Q2 and the final Qs are presented in the point representation, right? And then we just see the distance to get the answer. But the difference is to consider the quantifier, they started to support the reason. So obviously the seeds are in the point. By considering the win relation and citizen relation, we're getting some reason. And then this notations naturally support the intersection operator, because we just get the overlapped the square to get the intersection, and these are returned, and we see what kind of which entities are included in the overlapped square, and we get the final answer, right? And another approach is, so when you see this paper, so I couldn't include every detail. Everything is same. So, but we additionally introduced the notation of the square embedding. So different from the point-based embedding. So to represent square, we need to get the two information, right? The center information. Center, the point location, and these information. So the location of center and this offset vectors are needed to form the square, right? We assume that it is these information is used for here and here and here, and we can represent the square. And so we then this projection returns this two different information, and we get the box embedding, and we compute the overlapped position, and so on. And these are a simple idea, but more effectively solving the question. And one remaining thing in the first order query is to support this negative operator. So to respond, to get the president name who are in the Europe and in the country haven't held the World Cup yet. And to respond to the question, we need to use a negative negation operator. For the box embedding is not straightforward to represent the negation in because the negation of boxes, everything else is so every embedding should be form of the box. So these ones are not the box, right? So that's why they started to think about the probabilistic approach, and the idea is simple. So each entity is mapped onto some probabilistic distribution, and then going through the projection, and the result is the query, the temporal query is also presented in the probabilistic distribution, and the final location is here, and we see the difference between the potential entities and see the distance and get the final answer. For the beta distribution, so then we need to assume the basis, the probabilistic distribution, right? So we use the beta distribution. So it has benefit to present the negation. For example, so we have two parameters to get the beta distribution, and for the negation, we easily get the negation something like this. As far as I remember, so it is like the simple, the parameter flipping operation. So let me see. So negation is just from, so assume that the parameters are alpha and beta. So to get this, so we just use 1 over alpha, 1 over beta. So simply, and we get this negation distribution to the target embedding, and unions are from this. So yeah, to get the union embedding, they use the just pure the multi-layer perceptron. So for every projection, they use just the multi-layer perceptron instead of the just simple matrix multiplication, like multiplying W. They now trying to use the multi-layer perceptron to learn more complex the relationship. And for the intersection operator, they use a weighted linear interpolation, and for that they still use the multi-layer perceptron to decide the weight. And now we understand the negation operator, and by getting the final embedding, so which means we just have alpha and beta, and now we are able to see the distance between the candidate entities in this space. So this is a result. They to get this table, they are individually trained to respond to the question. So 1P represents one hop computation graph, and 3P represent this 3 hop path queries. And what else? So this means one intersection and one projection, and you have the 2 union, something like that. So unfortunately, they don't have generalized the embedding based the QA model. They individually learned to support the different types of queries, and the separately trained and get the result. The beta is the beta distributions approach. For the simple one, the other baselines are better, but when they have more length for the path queries and 2 intersection, 3 intersection, they are getting better and better in the more complex queries. The score is from the mean reciprocal rank, and 4 scores it means the highest scores. Okay. So today we have talked about knowledge-based Q&A techniques. So we also called the reasoning. So these are the state of the art. So as you see, they are still very simple and you're able to find many rooms to explore. So these approaches are published just last year. So you can try your own idea to support more diverse types of the relationships, and you can improve this model to support the more generalized the reasoning capabilities, to support the reasoning capabilities, right? All right, so this is the end of today's lecture. So when you have any questions, let me know. And thank you for your attention. Thank you very much. Bye-bye.